Okay, welcome everybody. I don't know if everybody's here, but we are recording it. Anybody have any logistics issues in terms of connecting, in terms of getting the resources on Sakai? Has that been working out okay, or is anybody having issues with that? Well, hearing none, um, I'm going to go ahead with today's topic. And let me see if that will actually work this time. Okay, so we are on, we are charging ahead to class number 2. We're talking about the discrete of how to, if you remember yesterday, my internet kind of was a bit unstable. I'm hoping it would be a little more stable today, and I just got a little message that says your internet is unstable. So if I freeze up or leave or something, then it's not by design, and I will try to get back online. Yesterday I had to restart my router, and miracles of modern technology. Anyway, today we're continuing with talking about the structure of discrete event simulation models. And today we're going to give some examples and actually kind of work through what how that works on a very simple little model. So to recap a little bit, discrete event simulation models involve parameters, state variables, and events. It is driven by something called the event list, and the event list is involved with a number of activities. The most important of which is keeping a list of all the known pending events in the future, and also having an algorithm that advances time, and it advances time to the next event instead of clicking along in a time step fashion. So again, we'll see some examples of this. So to recap a little bit, what is an event? An event is an interesting occurrence, and what's interesting? Really, the only interesting thing that happens in a state model is that the state changes value. In a discrete event model, the term for that is state transition. And so an event, among other things, involves defining what the state transition is. And this is something that the modeler defines. This is not something which is known or given beforehand. This is something that when you, the modeler, decide to create one of these models, then defining what the states are and then how they change, that is the events, the state transitions, that's something that you, the modeler, does. Now, one of the reasons why the time advance mechanism is important is that in between events, nothing happens. So in this world, in the simulated world, nothing happens, meaning that no state changes value between events. That is between the scheduled events, the events as they occur. Now, when an event occurs, after its two main functions are to perform its state transition, but then the second important one is to schedule other events. And it may schedule events, it may not schedule other events, it may conditionally schedule other events. Again, all of that will be made a little bit more clear as we look at examples. The other important thing is to remember is that the order of the events that as they occur are not necessarily the same as the order that they're scheduled. And again, we'll see that as it happens. And that's why the event list processing is so important. So when an event occurs, all it does is it puts, when it schedules events, it just puts events on the event list. And they may occur soon, they may occur in the future. The event that is scheduled may be the next event to occur, or there may be other events that have been previously scheduled that will occur first. And again, as we work through more examples today, and in the near future, you'll see how this works. Okay, so again, the event list keeps the pending events in the list. And it's also important to know that it doesn't keep all of the events that will ever occur in the simulation. It will only list the pending events. And the most important thing is just that the next event is on the list, because time is going to advance to that. And then after that, other events may be scheduled. And when an event is scheduled, the event list needs to make sure that those events are kept in the proper order. Again, one way to think of that is as a sorted set, because in the implementation, that's literally what it is. And it's kept in sorted order of the scheduled time. Again, the way time advances, it advances to the next scheduled event. And that actually may be a 0 amount of time, or it may be a longer amount of time, but it is not typically a fixed amount of time as it is in a time step model. So we advance time to the next event. It removes the event and then processes the event, meaning that it performs the state transition and then schedules whatever other events that event has been defined to occur. And it just keeps doing this, and as long as the event list, as long as there's more events to process. So now, how do you start up? Well, initially the event list is empty, and so if you were to just blindly execute that rule, then it would immediately end. So what you need is at least one initial event, and we call that event the run event, and that's like the main event in programming languages like Java. But the run event is always scheduled to occur at time 0. And like other events, though, what the run event does is always up to the modeler. What the run event is responsible for, and we'll get into this a little bit more, especially as we start implementing models. The run event has 2 primary responsibilities. One is to initialize all of the state variables. In other words, its state transition is to take every state variable and set it to its initial value. The second responsibility of the run event is to schedule any initial events. Again, if you think about it, after the run event is finished, if it doesn't schedule any more events, then the simulation immediately ends. So that's not very interesting. Now, again, as a modeler, it will be your responsibility to define what these events do. That's really what how you create this. And to create a discrete event simulation model, we define the parameters, which are the values that do not change throughout a given simulation run. We'll see some examples of that. State variables are the ones that typically do change. Just by chance, since there's randomness often involved, and we'll see more of that as the course unfolds. Because of randomness, it may be just by chance that one state variable may not actually change value, but it always has to have the potential of changing values. In other words, you may have a state that for some reason the event that causes its state transition just never happens to occur. And that's a possibility. Again, not terribly likely, especially in the long simulation runs that we will typically want to do to get valid statistics. But anyway, the state variables, again, those are things that the modeler defines. And when I say modeler, I mean you. And then events. Although in the beginning, it'll be me, but then as we go on, you're going to be responsible for creating discrete event models, designing them, that is by defining all these things, the parameters, state variables, the events, meaning the state transitions, and the scheduling relationships, that is which events schedule other events. Okay, so we saw an example yesterday of this arrival process. And so the idea is that the idea for this is that you just have, so in a way, this is kind of the hello world of discrete event models. It's the simplest possible one. It has one parameter, which consists of a sequence of inter-arrival times. It has one state, which is just the number of arrivals, which is initially 0. And every time we get one of these arrival events, we're just going to increment this arrival counter. So the two events are the run event. Again, you always have a run event. And its responsibility is to initialize state variables. So it sets n equals 0, which is the initial value. And it schedules the first arrival. And then when the arrival event occurs, it simply increments the number of arrivals, that is the state variable n, and schedules the next arrival. Now, a slightly more interesting example is something which is called the multiple server queue. And the idea here is that you have things that are customers, and that the customers are in quotes because the customers could be literal customers, like arriving to a restaurant or a bank or any kind of facility. And like a bank, if you've actually been in a bank lately, instead of doing everything online, when you go, there are typically a bank, as it were, of tellers. That is a number of tellers, but there's a single line, and there's like a little rope where you have a single line, you stand in line, and then however many tellers there are, that is servers, they serve the next one in line there. If you remember what it was like to travel, again, to kind of putting aside the premier lines and everything, the normal ticket lines act pretty much the same way. You know, everybody waits in one queue. A queue is just a fancy word for waiting in line. And when a server completes service, they will start on the next available customer. And then the customers kind of arrive actually according to something like an arrival process. Just as an aside, one of the things I like about the word queue is it's really just the letter Q followed by 4 vowels waiting in line. So anyway, so here's an example of a model for this multiple server queue. And the idea is we have these parameters, which are first the inter-arrival times. Those are the times in between which customers arrive. And that's just some sequence of numbers. When we implement it, that is typically generated by a random sequence, but it need not be. Likewise, we have service times. That's how long each customer is going to take. And again, that's just some sequence of numbers. And so these are, because those are just numbers that are not affected by the model, those are actually parameters. And then the final parameter for this model is K, which is the number of servers, as how many we have. So the reason that's useful is that the same model can work with any number of servers. So we don't have to create a separate model for one server or a separate model for 2 servers, et cetera. We just change the value of K. All right, now we have 3 state variables for this. 2 of which are kind of intrinsic and 1 which is kind of derived. So the first state variable is going to be the number in the queue. So when we start off, there's going to be nobody in the queue. And every time somebody shows up, we're just going to increment that. We'll see how that works with the event. The second state variable is going to be the number of available servers. That is the number of servers that are not serving anybody. And the initial value of S, the number of available servers, is going to be K, the number of servers. So in the beginning, our system is empty and idle. And so all of the servers that we have are going to be available. For this particular model, the servers never get a break. We're never going to add or subtract servers. Again, that's a characteristic of this model. We could make it more complicated, but again, we're going to start simple. And the final state variable is the number in the system. And the thing about that state variables is that actually is not an independent variable from the other two. In other words, if we know the number of servers and you know the number in the queue and the number of available servers, then you know exactly what the value of the number in the system is. And that is the number in the queue plus K minus S. So if we have K total servers and S are available, then K minus S are busy. And we'll see how that works. Now, the events are, we're going to have 4 events. Again, the run event, the purpose is to initialize our state variables. So we're going to set Q equals 0 and S equal K. And note that I haven't set the value of L because L is going to be based upon this formula. Oops. This relationship between the state variables and the parameter K. So we don't need to initialize it. In fact, we typically don't want to have states that depend on others that independently change their value. But the run event is going to set Q to 0 and S to K. And we'll schedule the first arrival with a delay of T sub A. So remember, T sub A was our inter-arrival time. So we pick off the first, notice the curly brace shows that that's going to be a sequence of these things. And so, but we just pick off the first one in this particular case. So every time that we say, in this case, T sub A, we'll just pick off the next one. So the event that we're calling arrival here, and again, this is important to understand that this is different than the arrival event in the arrival process that we talked about before, even though it may look a little similar. So its state transition is to increment Q. It's going to set Q equal to Q plus 1. So when somebody shows up, we're just going to put them in the queue. And this is kind of like when you enter the facility, you actually first have to go into that line. So now the thing is that if we show up and a server is available, then we can actually schedule the start service. And we're going to schedule that with a delay of 0. And you may be thinking, well, it takes a certain amount of time to get from the queue to the server. And then that's true. But for the purposes of this model, we're just going to treat that as 0. We can sort of talk about that, what some of the assumptions of the model are after we go through this. And then the arrival event is going to schedule the next arrival with a delay of the next inter-arrival time. So the arrival event has one state, has the state transition, we're incrementing Q, and it could possibly schedule 2 events. Now, the start service event, that is the event that says, well, the server is going to start service. So what does that do? That does 2 things to our state. Informally, you take somebody out of the queue and you remove one of the available servers. So the state transition for that would be Q is Q minus 1 and S is S minus 1. In other words, there's 1 fewer in the queue and we have 1 fewer available servers. And what the start service event does in terms of scheduling, it's going to schedule the end service after a delay of T sub S. And remember that T sub S was our sequence of service times. So T sub S just picks off the next service time and says, this is how long this customer is going to spend in service. And finally, the end service event says, okay, now what does this represent in the system? It represents the customer who has finished service. And what happens there? Well, basically only one thing. We now have the server who was busy is now available. In terms of the model, what does that mean? That means that S is 1 greater than it was before. So if there were, say, 2 available servers before, now there are 3. If there were none before, now there's 1. Again, whatever that was. But then the question is, what does the server do next? Well, if you're the next one waiting in the queue, then you want to be waited on. And so the condition for that is that if there's somebody in the queue, then that server will start scheduling them, or start working on them. In the model, that says a customer in the queue is the statement queue is bigger than 0. And so if that is true, that is, if there's somebody in the queue, then we'll schedule another start service with a delay of 0. And when that start service occurs, that's going to perform the state transition there. So the important thing to understand is that when you define these events and state transitions, you want to make sure that they stay in their own lanes. In other words, this end service event, even though looking at the model, you may know that there's somebody in the queue and you know that they're going to serve them next, the end service event that's not its job. Its only job is to perform state transition and possibly schedule the next start service. And when we look at our example, this will hopefully make this a little more clear. So what we're going to do, is execute. Basically, we're going to be the event list for this model. And for the parameters for this model, I've chosen a k equals 1. That is, we have a single server. And we have the following inter-arrival times. Now, it's important to understand these are the inter-arrival times, not the absolute times. We'll see how that works out once we start looking at the numbers. So our inter-arrival time, the first inter-arrival time is 2.1. The next one is 1.4. And what that says is the time between when the first customer and the second customer arrives is going to be 1.4 simulated time units. And the time between when the second and the third one arrives is going to be 3.5 simulated time units. Similarly, the service time for the first customer served is going to be 2.2 time units. And the service time for the second customer is going to be 1.3. And in a model, a typical model, you're going to have many, many more numbers. And that's why we have the ... So there's going to be more. But since we're doing it by hand, we're just going to, just to show how the event list works and how these state transitions operate, with the objective of eventually extracting some statistics from this model, which we'll talk about a little bit more tomorrow. So in this particular case, we're just going to simulate for 2 customers completing service. That is, we're going to have 2 end service events, and then we're going to stop it there. Once we start implementing it on the computer, then we'll see various ways of ending the simulation. Okay. So the way that the simulation starts is that we always begin with things basically undefined. So we will begin with the state before the simulation even begins. The world does not get created until the run event happens. And so what we begin with is a current time. We're going to list in this little sequence of tableaus. We're going to list the current time, the current event, what the value of our 3 state variables are, Q, S, and L. Remember, Q is the number in the queue, S the number of available servers, and L the number in the system. And then the event list, we're going to keep track of what the pending events are. And for this small example, the event list is never going to have more than a couple of events on it. But it always starts, regardless, we're going to always start like this, with things undefined, but the run event on the event list at time 0. And again, that's similar to, say, a Java program right before it executes the main event, the main method. Okay. Now, what the event list does, remember, is it advances time to the next event. So when we execute the run event, well, when we perform the event list what the event list does, we advance time to the next scheduled event. In this case, the next scheduled event is at time 0. And so we take the earliest scheduled event, in this case, the run event at time 0, and we simply say, all right, now our current time is whenever that event was scheduled to occur, and now that becomes the current event. The second thing we do is we perform the state transitions. Now the state transition for the run event is to initialize our state variables. So it sets Q is equal to Q to 0 and S to 1. And then we can compute L to be K minus S plus Q. And that turns out to be 0. In other words, Q is 0, S is 1, and L, according to that equation, is now 0. So that's the state transition. And then the third thing is we schedule any possible events. So what was the rule for run? Run scheduled the first arrival with the delay of the next T sub A value. Remember, the first T sub A value was 2.1. And so it schedules the arrival event and just puts it on the event list at time now, which is time 0, plus that delay to 2.1. And so we schedule arrival at time 2.1. And so after this first iteration, this is the status of the simulation. So it has just completed the run event. Its current time is 0. The values of its states are Q is 0, S is 1, and L is 0. And the event list consists of a single event, the arrival event, scheduled at time 2.1. That's what the status of the simulation is. Everything prior to that is basically gone. That's important to understand when we're doing it by hand. On the computer, it will kind of enforce that. Okay, so we're now finished with one iteration. Now, let's execute the next thing, the next event. So what does that do? That advances time to the next scheduled event. In that case, our next scheduled event is this arrival event that occurs at time 2.1. So notice that we skip over, we don't say, well, we're gonna, since our time have, the decimals on our time are in tenths, we don't say, okay, time 0.1, 0.2, or, no, we just advance, skip over all that. We advance to time 2.1 and we execute the arrival event. Okay, that's the first step. Next step is we perform the state transitions. Now, the state transition for the arrival event is actually just Q is equal to 1. S maintains its old value, 1, and L is now computed to be K minus S plus Q, which is 1 plus 1 minus 1, which is 1. So after the state transition for the arrival, which actually was just Q is 0 plus 1, we now are in that condition. And then finally, we schedule any events. So the first is we have an arrival. Now the arrival occurs with a delay of the next T sub A time unit. So if you remember, that was 1.4. And so the next arrival event is going to be scheduled at time 2.1, the current time, plus 1.4, the delay, or 3.5. And so we see that the arrival event is scheduled at time 3.5. But then, because S is bigger than 0, we schedule a start service with a delay of 0. And that's scheduled at time 2.1 plus 0, or 2.1. And so now the state of the event list is we now have 2 events. Notice that the order that we scheduled these events in is unimportant. The important thing, so in this particular case, we scheduled the arrival event first, and then we scheduled the start service, but that doesn't matter. What matters is that the time they are scheduled to occur. So in this case, regardless of the order that we scheduled them in, the start service event is scheduled to occur first, that is at time 2.1. The next arrival event at 3.5 is going to happen sometime later. So now the status of the simulation is the current time is now 2.1. We've just executed the arrival event. The state variables are ones all the way across, and there are 2 events on the event list. We have 2.1, a start service, and 3.5, an arrival event. What happened before, everything that happened before is now forgotten as far as, at least as far as the simulation is concerned. This is where it is. All right, so now let's look at the next one would be, oops, well, okay, so I don't have the little, hopefully you get the idea. So now, okay, so remember these were our service times, and okay, that's a typo. That should be just 2.2. I forgot. I don't know how the 3 got in there. Okay, so we are right here. We advance time to the next event, which is 2.1 start service. We perform its state transition, which, if you remember, is Q minus 1 and S is S minus 1. So now Q becomes 0 and S becomes 0. But L, if we apply the equation, is K minus Q plus K minus S plus Q. So K is 1 minus S 0 plus 0 is still 1. Now, the end service event is scheduled at time now, which is 2.1, plus the next service time, which is 2.2, and that is 4.3. And so we see an end service event has now been added to the event list at time 4.3. But now this is very important. The arrival event, this 3.5, that isn't going anywhere. The only event that gets removed from the event list is the one at the very top that we pulled off. So when you're working, I'm going to, at some point very soon, starting tomorrow, I'm going to have you guys do this yourself. And it's important not to lose any events. And so now the state of the simulation is it's time 2.1. The start service event has just occurred. These are our state variables, 0, 0, and 1. And the event list has 2 events on it, an arrival at time 3.5 and an end service at time 4.3. And we just keep chugging along. So at the second arrival event, okay, now here's where, again, we were here, time 3.5, advance time to 3.5. The event is arrival. What does arrival do? It just increments Q by 1. It does not do anything to S, to the number of available servers. But the formula for L now, remember, it's K minus S plus Q. So K is 1, still 1, minus 0 is 1, plus Q is 1, which makes it 2. And just verify that for yourself. Now, the thing is, as the arrival event, remember, the first time it occurred, we scheduled 2 events, the next arrival event and the start service event. But we only schedule the start service event if a server is available. That is, if S is bigger than 0. Because S is equal to 0, that is false. So we do not schedule the start service event when an arrival occurs and S is 0. But we do schedule the next arrival event, and it's now 3.5. Actually, the next, by coincidence, the next inter-arrival time was also 3.5. And so that means that there's going to be an arrival event at time 7. Now, just turning the crank, we have 4.3. The next end service event was scheduled. And all that does, remember, that only increments S. Its state transition is S is equal to S plus 1. And so it doesn't do anything to Q, but remember L, which depends on Q and S, is now back to 1. So, and intuitively, we had two in the system. We had one that was being served, one that was in the queue. The one that was being served left, and then now we're back to just one. And since now, when we have an end service, intuitively or informally, if you're the server, if there's somebody in the queue, you want to serve them. In the model, that is the start service event. And so we simply schedule the next start service event with a delay of 0 because Q is bigger than 0. Where are we here? Okay, so our second start service event, again, see, I hope you're getting the idea that we're just simply, we're simply blindly executing an algorithm, which is to advance time to the next event, which in this case, 4.3. The advance is 0, but who cares? As long as the advance is not negative, we can't go back in time. The start service event, remember, it decrements Q, so Q goes from 1 to 0. It decrements S goes from 1 to 0. The formula for L is the values have changed, but the value of L hasn't changed. And the start service event, the next service time is 1.3. And so 1.3 plus 4.3 is 5.6. So it will schedule the next end service event at time 5.6. And again, this arrival at time 7 is not affected. And turning the crank again for the final time, we have that we have an end service event. Again, advanced time to 5.6 end service event. All it does is increment S to 1. What is the condition? If Q is bigger than 0, it will schedule a start service event, but Q is 0, so it doesn't schedule anything. So in this particular case, the end service event has not scheduled any event, just by chance. And so now the final state of our simulation is that there's still an event, an arrival event that's scheduled to occur at time 7 in the future. But for our purposes, we're more or less finished. Okay, so it's the final state of our simulation. If our rule was we're going to run the simulation until we had 2 service completions for our customers, and we've done that. The state of the simulation now. Because we are doing this by hand, if we look at this final tableau, we see the sequence of how things evolved. That is, we started with the run event and nothing defined. And then we just kind of, every one of these lines, and this is the reason why they're separated by a little bit of space, every time there's an iteration, the simulation status would move to one of these lines. That is, at the end, the simulation doesn't have all of this information. At the end, the simulation just knows this. It knows that it's time 5.6. It knows that the state variables have Q0, S1, and L0, and that at this particular time, there is still an arrival event at time 7. And if we have decided that this is going to be the stopping criterion, that is, we're going to end it after 2 end service events, there's one here and one here, then we're basically done. And in the implementation, we could specify that, and then what would happen is at this point, when that second end service would happen, it would actually go in and just delete the event list. Basically clear it out. Okay, so what's important here is to understand that what we have done is we have now basically created our state trajectories. Now, in looking at this, since we're doing this kind of by hand, as it were, we can kind of look at this tableau, we look at the entire sequence of things. And if we were to graph what's going on here, we see that for each of our state variables, at time 0, Q is 0. At time 2.1, it became 1 and then went back down to 0. And then 3.5 became 1, 4.3 became 1, etc. So for our 3 state variables, we have our state trajectories. And from those state trajectories, we can extract our statistics. That is what we want to find out about this model. I mean, what might you want to know about this, about a model like this? Well, statistically, with only two observations, we're not going to get anything of great validity, which is why we ultimately will have to do this on the computer. But the thing is here that notice that we've done this entirely by hand. And that our model, if we kind of go back to, our model, let's go back to our model. Okay, we defined our model in terms of these parameters and state variables. The most important thing was we defined our events as these 4 events. We had our run event, but the most important ones is that once things started kicking off, we had the arrival events that had these conditions. We had state transitions and then the scheduling rules. And then for the start service event, again, we just had these state transitions and the scheduling rules. And every time an event occurs, it's important to just do what's on that event and not try to do anything more. This thing keeps stopping all right, so let's, okay, so in looking at this entire tableau, we can kind of figure things out. But on the computer, if we were running this on the computer at time 5.6, this would be all we know. All we would know is that it's now time 5.6. These are our states, and if we stopped it here, the event list would actually be empty. So on the computer, we don't know any of this. So therefore, we need some way of capturing this data as it shows up in some way. And and I believe everybody, if you remember that little simple statistics program that I tortured you with a while back, the idea on that was that it would be getting its data one observation at a time. And if you think about how a simulation works, that's exactly how this is going to work. In other words, as these state variables change value, they're going to be dishing out these values one at a time. And when we start implementing it, which will be actually on Thursday, we'll see how the way of implementing it emphasizes how that goes. Okay. So that is today's topic. Now for tomorrow, what I'm going to ask you to do is read the next section, especially about how to the difference between time varying and tally statistics. The reason that's important is because for these variables, Q and S and L that we have here, if we want to find out what, say, the average number in Q is for over the length of our simulation. We actually can't do it in the standard way that you learned in your stats class. That is, we can't just simply add them up and divide by the number. We actually need to do a time varying average. So read about that tomorrow, and we will we'll talk about how that applies to this particular situation.